Okay, so we are going to start our session. This is week 7 Sensor and Actuator problem solving session. I'm ARPITA BISWAS. This is about me. I'm ARPITA BISWAS, the student of PhD in Electrical Engineering Department. I'm from Indian Institute of Technology, Jodhpur, and this is my educational background. That I did my MTech from IIT Jabalpur in Micro Nano Electronics, and I did my BTech from Maulana Abul Kalam Azad Institute of Technology in Electronics and Communication Engineering. And this is a site from where you can get more details about me. And the class schedule is every Tuesday 7 to 9 p.m. So in this session we are going to discuss some question answer, and if you have any doubt then you can ask me. And so let's start the session. So this is the question number 1. So at first you go through the question carefully, then you think and try to give the answer. And if you are not able to give the answer, then I will explain what is the right answer, and at least you can try now. So the first question is, consider the following statement with respect to the multi-channel peristaltic pump discussed in the course. Statement 1 is, well, the 4 channels in the multi-channel peristaltic pump can circulate or flow liquid at the same flow rate only. And the statement 2 is, the minimum flow rate possible in the channel is in the range of milliliter per minute. So which of the above statement are correct? The first answer is statement 1 only, and the second option is statement 2 only, and the third option is both statement 1 and statement 2 are correct, and the fourth option is neither statement 1 or nor statement 2 are correct. So at first go through the question carefully and try to give the answer. At least try now. Take some time.
Both the statements are wrong.
Why?
peristaltic pump, the fluid can flow at different rate. You can modify using that machine. In
Okay.
statement 2, it is said that it's milliliter. It's actually not. It's like microliter per minute.
Yes. And what about Banana Sindhu?
Hmm? What?
Uh, I'm not talking with you. Actually, there are one student, na? Banana Sindhu. Banana Sindhu? I'm audible?
Ma'am, I think option one, ma'am. This one only.
Why option 1?
In peristaltic pump, all the fluids can flow through it, ma'am.
Okay. And what about this next statement?
Actually, in statement 1, we can modify the flow rate for each. So, next one.
Okay, actually, here I want to know each and from each and every student now. So if they are doing some mistake, then we can explain them.
Yes, ma'am. In
Okay.
that video, they showed the demonstration of each of the one is spinning at different speeds, so we can modify the flow rate.
Okay, I'm getting your answer. So now I'm asking to Banala Sindhu why statement 1 is correct and why not statement 2.
Ma'am, in the channel, the flow rate will be all types of liquids can flow, ma'am. But they said minimum flow rate is possible in the range. You can flow, ma'am.
So option 1 is not correct, na? Go through the question carefully. All the 4 channel in the multi-channel peristaltic pump can circulate or flow liquid at the same flow rate only. So this statement is wrong. And what about the second statement?
The milliliter per minute, so it's not actually it's microliter.
Okay. And what about Banala Sindhu? The flow rate is in milliliter or microliter per minute? I need the answer from all the students now. At least try. Banala Sindhu.
Ma'am, I think first option, ma'am.
First option is S1 only.
Yes, ma'am.
No, S1 is wrong na. Because the flow rate is different. And also in the second statement, the minimum flow rate possible in the channel is in the range of microliter per minute. So both of statements are wrong. So option 4, neither S1 nor S2 are correct, is the right answer. Okay.
Yes, ma'am.
Yes, you are right, Suthar. So we are moving towards the next question. Actually, I'm actually I'm taking all of your answer. Then If anyone have any doubt, then we can explain. Okay.
Yes, ma'am.
Okay, ma'am.
So this is question number 2. Evaluate whether the below statement is true or false. Sputter deposition is performed at a lower pressure than thermal or E-beam evaporation. So the statement is true or false. Take your time, then try to give the answer.
So is false, ma'am.
Why? Have you heard about the thermal evaporation or E-beam evaporation?
Yes, ma'am.
What happened in E-beam evaporation?
In E-beam evaporation, basically we electron beams, right? So
Yes.
we will the electron beam is created from a filament, and it is diverted through some magnetic fields. It will strike the crucible, and that crucible will make and evaporate and deposit on the
Okay, and what about thermal?
thermal. We have a source folder and a source. So basically, to evaporate, we will keep the source folder, so that the source folder temperature should be higher than the source itself. When the temperature of the source become high, the source will evaporate and it will be concentrated. We can modify the pressure accordingly so that the substrate will get coated appropriately.
And what happened in sputter deposition?
Basically, during sputtering, we will using the organic gas at a high temperature, right? And we will dislodge the atom. We will dislodge the atom, and that atom will get deposited on the substrate.
So sputter deposition is performed at lower pressure than thermal evaporation. So what is the right answer?
Basically, sputtering is carried at high pressure, right? High pressure, and first the chamber is made vacuum, and then the
Yes.
organ molecules are enter into the chamber to make it at high pressure. So sputtering deposition is take place at high pressure.
Okay, and
Is it right answer?
uh, just wait a minute. Banana Sindhu, what is the right answer?
Ma'am, false, ma'am.
Why?
Ma'am, evaporation takes at any temperature, ma'am. It takes place in any temperature. When molecules strikes the surface, they are going to import some energy to water molecules. So then,
Here we are talking about the pressure, na? Sputter deposition is performed at lower pressure than thermal or E-beam evaporation, because this all three deposition process is PVD, physical vapor deposition technique. So here we are discussing about the pressure. Yes, the answer is false, but my question is why?
Because the answer is obvious that for sputtering we need to create the environment, right?
Yes.
To dislodge the atoms. And for thermal, it is not mandatory to create the environment. Create the environment in sputtering, we will first make it as vacuum, and by making it as vacuum, the pressure will be dropped so that the normal air molecules will be heated. And then we will go for argon or xenon gases.
Yes, Sudhir, you are right. The answer is
Okay.
false and the explanation also right. Okay.
Yes, ma'am.
So Banana Sindhu, you got the answer?
Yes, ma'am.
Why we need high pressure in sputter deposition?
Yeah, but I have one doubt.
Okay.
Do we need to control pressure for thermal evaporation?
Yes. When we go for the thermal evaporation deposition, in that time also we we did some 10 to the power minus 6 millibar pressure. So we need a constant pressure for uniformly deposition.
And for e-beam,
I think E-beam also we want the control. There I think we need some. You have told me earlier, na, the total environment we need. In that environment, we can take this E-beam and also we can deposit that material onto the substrate. So I think in physical vapor deposition we have to maintain the environment. That's why we need to take we need this particular constant pressure, and we have to maintain the lower pressure, sorry, the higher pressure.
so basically sputtering requires higher pressure than e-beam or thermal. But now basically PVD requires some kind of environment changes.
Yes, yes.
Okay.
So next we are moving towards our question number 3. Which of the below statement is false? So first statement is thermal evaporation heat the crucible as well as the source material kept inside it. The second question is E-beam evaporation has more chances of impurities getting deposited through the diffusion from the crucible material. Then the third option is sometimes plasma cleaning is used prior to thermal evaporation. And the fourth option is low vacuum is used to ensure uniform deposition of film. So at first go through the question carefully, then try to give the answer.
Basically, the option 1 is, I think, true. Thermal evaporation heats the crucible and the source material.
Okay. Okay.
It's true. Small chance of the impurities.
Banana Sindhu, go through the question carefully, and I need the answer from you also.
I think option 4 is the false one.
And why option 4?
Because in first option, we basically for thermal evaporation, both the crucible as well as source will be heated, right? So
Okay.
that statement is true. Second one, E-beam evaporation has more chance of impurities. I think that one is false actually. For E-beam, doing a preparation.
Actually, in option 4, what is telling low vacuum is used ensure a uniform deposition. Low vacuum means high pressure. It means 10 to the power minus 6 or something like that. Okay.
Okay, okay. So you are saying low vacuum means high pressure.
It's mean 10 to the power minus 6 range or 10 to the power minus 8.
So basically, in third option, the plasma cleaning is applied for substrate, right? Something.
Yes.
Oxygen plasma, we use it to clean. Use the oxygen plasma for cleaning.
Okay.
I think option 3 is also true. So I had doubt in second or fourth option.
Meghna, what is the right answer? Javira, at least try. Banana Sindhu, please unmute yourself and try to give the answer. You can take your time. Yes, what is the right answer?
I'll go with sometimes plasma cleaning is used where the thermal evaporation.
Here the question is which of the below statement is false?
The second one is true, ma'am.
How second one is true? Can you explain please?
I'm just asking you, ma'am. I have a doubt on it.
Take your time and go through the question carefully now. What happened in E-beam evaporation?
Ma'am, second option false, ma'am.
Can you explain why?
E-beam evaporation is used to evaporate at high energy electrons, ma'am.
Yes.
In that, sufficient energy is used for evaporating any material, ma'am. So there is no chance of diffusion of crucial material, ma'am.
Yes. So here right answer is option 2. E-beam evaporation has more chances of impurities getting deposited through the diffusion from the crucible material. Crucible is the substrate holder, na? So here what is saying, from the substrate holder to the material which will be deposited, here the impurity is adding. So in E-beam evaporation what happened? In the particular portion where E-beam is going, and from there is only the material is evaporated and deposited on the substrate. So there is no less possibility that from the crucible or the substrate holder to the material which will deposited, na? So there is less chances of adding this impurity or the diffusion from the substrate holder or the crucible to that source material. That's why we are using the That's why we are using this E-beam evaporation. And low vacuum means the mean free path is in 10 to the power minus 4 to 10 to the power minus 8. That's why low vacuum means the higher pressure. So the fourth option is also right, and sometime plasma cleaning is used prior to thermal evaporation. This option is also right. So option B is the right answer. It means it is the false statement. Okay. So this is our question number 5. Evaluate whether the statement given is true or false. So the first option is IR-based distance sensor work on the principle of reflectance from a subsurface. So is it true or false? So at first go through the question carefully and take some time, then try to give the answer. I am coming back in 2 minutes. Just go through the question. So what is the right answer? Hello. Banana Sindhu.
Ma'am, false, ma'am.
Can you explain why?
Ma'am, infrared sensors works on the principle of reflected light waves, ma'am.
IR-based distance sensor work on the principle of reflectance from a surface. Suthar, what is the right answer?
Yes, ma'am, based on the reflectance, it will get changed.
Yes, it is true. Because in the IR-based distance sensor, there is a two type of LEDs present. One is lighter or white color, and one is black. So the transparent color is transmitter, like it acts as a transmitter, and the black one is acts as a receiver. So when the light is IR light is coming from the transparent one, the white one, so it goes to the surface of a substrate, and from that it reflects and it received by the receiver. So the in the IR based distance sensor, it's work on the principle of reflectance from a surface. So the statement is true. Javira, have you got the answer? Next we are moving toward question number 6. Which among the following are the way in which microfluidic membrane made from PDMS can be bonded to glass substrate? The first option is UV adhesive curing. Second is oxygen plasma activation and bonding. And the third option is using transparent double-sided adhesive. And the fourth option is all of the above. So take your time and then try to give the answer. And I need from all of you. I expect that all of you at least try. Please go through the question carefully and try to give the answer. Which among the following are the way in which a microfluidic membrane made from PDMS can be bonded to glass substrate?
All the above.
Can you explain why?
Oxygen plasma is used for making microfluid chips, and other three options also use it to bond microfluid.
Okay. And when the UV adhesive curing is needed? Banana Sindhu. What is the right answer?
I think all of the above, ma'am.
Can you explain? Can you tell me when we go for the PDMS, when the fabricate the microfluidic membrane made from the PDMS, then what is the first stage? How we fabricate this type of microfluidic devices? Suthan? How we will fabricate a microfluidic membrane which is made from PDMS? Have you heard about mold, silicon mold?
Silicon
Mold.
mold. No.
That type of shape is present now, like that type of shape is present. So where we actually first using the lithography, we make a structure on the silicon wafer, and then there the PDMS is using, and from where PDMS. Hello? Yes. Okay. So can you explain here? So this step will clear.
Which one, ma'am? Which one to explain?
How to fabricate a microfluidic membrane made from the PDMS. Whatever I am telling now, that the silicon mold, then PDMS is deposited, or then curing the PDMS from the silicon mold.
Yes, ma'am. So basically, we will create the mold as we said, using the various techniques, right? Using the photoresist and using UV light and developing. We will create the mold, and after that, we will deposit the PDMS such that the PDMS will operate evenly in the mold. After
Yes.
that, I think after that we use
Then we curing the PDMS from the silicon mold. So there is a channel type portion in the PDMS. Then we need to bond this PDMS to the glass substrate or something else. So in that case we need the oxygen plasma. So at first we have to cure the PDMS from the silicon mold. Then we need the oxygen plasma to make the bond between the glass substrate or something, or substrate if we used. Then we have to make the bond. Then actually using the transparent double-sided adhesive. So in that case, if we use the if we see the microfluidic membrane, in that case you can see it is transparent. So some PMMA or something like that is used there. So this is transparent. So the right answer is all of the above. So the next question is, which among the following material can be used for making the microfluidic channel? The first option is PDMS, second option is PMMA, and the third option is paper, and the fourth option is all of the above. So please take your time and try to give the right answer.
I think we use both PDMS and PMMA.
And any other answer? Banana Sindhu?
Not sure about that.
Banana Sindhu? at least try. Banana Sindhu.
Ma'am, I think PDMS, ma'am.
Yes, PDMS, PMMA and paper. All the three are used for the making microfluidic channel. Okay.
Paper is also used there, ma'am.
Yes, yes.
For microfluidic, paper won't get dissolved.
You can recheck it. All the three are used for microfluidic channel. Now we are coming.
But in the video, they have not mentioned that paper is also used for microfluidic.
From the others video, actually yes, in the video it is mentioned about the PDMS, right? So you can
Yes,
also recheck
In the
that.
video, only PMMA and PDMS are mentioned, not paper.
Okay, but you can recheck from the internet, no? Now we are coming to the question number 8. Which among the following statements are false? A perfect black body absorbs all incoming light and does not reflect any. The second option is an IR-based distance sensor has the highest sensitivity when the target surface is a perfect black body. And the third option is an IR-based distance sensor has higher sensitivity when the target surface has lower absorbance than the reflectance. And the last option is the Planck's law is associated with black body radiations. So which statement is false?
first option is true, ma'am.
Okay. Here the question is, which among the following statements are false? Go through the question carefully. Banana Sindhu, what is the right answer?
Ma'am, I think third option, ma'am.
Can I explain? And what about the second option?
Second option right, ma'am.
An IR-based distance sensor has highest sensitivity when the target surface is perfect black body. So when the surface is perfect black body, so what about the reflectance? Like here the light is
Perfect
coming.
black
Then
body.
from the surface, if it is totally black body, it will absorb the IR
Yes,
radiation or IR
total
light.
radiation
Then
it absorbs, ma'am.
okay. So if it is,
When body is perfect black body, it absorbs total radiation, ma'am.
yes,
Without uh,
then
without any
what
reflections,
about
it
the
absorbs.
received signal? Because here the transmitter, so it is giving the signal to that black body. Then if it is absorbed now, so nothing reflects from that now. So receiver will receive nothing, or less amount of. If it is perfect, then nothing it will receive. So then what about the sensitivity? So sir,
Sensitivity will be increased.
how the sensitivity will increase if the substrate is perfect black body?
No, the sensitivity will be decreased because the black body absorb all the radiation.
And nothing will go to the receiver now.
Yeah.
So what is the right answer here? Yes, option 2 is the right answer. Next question is, Banana Sindhu, have you got the answer? Do you have any doubt?
Yes, ma'am.
So we are moving towards the question number 9. Which among the following statements are true about the thermal evaporation process? Statement 1 is the thermal evaporation process heat only the source material and not the crucible. And the second statement is plasma cleaning must not be used prior to the actual thermal evaporation process. So the first option is only S1, and the second option is only S2, and the third option is both S1 and S2, and the fourth option is neither S1 nor S2. So please go through the question carefully and try to make the answer. Go through the question carefully and try to give the answer.
Basically, option 1 is only the source material not crucible. That is actually false. The plasma cleaning must not be used that also falls. So there is some more.
And banana Sindhu. What is the right answer?
Ma'am, neither S1 or S2.
Okay. So the right answer is neither S1 nor S2. So what happened for thermal evaporation process? Sudhir?
Thermal evaporation, basically we heat the crucible. No? By heating the crucible, it is similar to like boiling the water to the pot. By
Yes.
heating the crucible, the source material in the crucible will also get heated and it will get deposited on the substrate.
Okay.
So the first one is false.
And the second is also false. The right answer is option B. Next, we are moving towards question number 10. With respect to PVD, evaluate whether the below statement is true or false. The source material is only deposited on the target substrate and does not contaminate any other part of the chamber. So it is true or false. Please go through the question
Yes.
carefully.
False.
Banana Sindhu.
Just a minute.
Take your time and try to answer.
False, ma'am.
Now, can you explain why false?
Consider the sputtering process. Basically, it will contaminate the other parts of the chamber.
Okay.
Heating also. So that's why here it is mentioned basically PVD, which includes medium sputtering and thermal tube.
Thermal
So
evaporation.
in this regard, it is false.
Yes. Banana Sindhu, have you got the answer? Banana Sindhu, is it clear to you? So next we are moving toward the question number 11. Which one is correct? Here the multiple option can correct. So the first option is source holder material melting point should be lower than the source material melting point. Second option is source holder material melting point should be equal to the source material melting point. And the third option is source holder material melting point should be extremely higher than the source material melting point. Or the fourth option is none of the above. So go through the question at first carefully. Here multiple option can be right.
Only option 3.
Ma'am, option 2 and 3 right now.
Basically, when you have the source holder and source material at equal melting point, both will be melted, right? So
Yes.
there is nothing is holding the source material itself. So in that regard, the source holder should be greater than the source material itself. So only option 3.
Yes. Banana Sindhu, have you got the answer? Actually, if the source holder and the material which we want to deposit, if the melting point will equal or the source holder melting point is lower than the material which we want to deposit, then what happen? The source holder material will try to evaporate and it will deposit it. so we are not getting whatever material we want to deposit. Okay, that's why the source solder material melting point should be extremely higher than the source material. So it can so only when we heat the source solder material, then it only evaporate the source material which we want to deposit to the substrate. That's why only the third option is right here. Good. Now coming to the next question. What happens if the source material melting point is close to or equal to the source material melting point, and what is the alternative? So I think we were already discussed in the previous question. So now the question is, what is the alternative? Which process we will use?
We can use the UV.
Why? Actually, I am asking about the basic principle of E-beam, how the E-beam is operated.
So E-beam, we will the E-beam basically electrons, right? So electrons are produced to a filament, and we have an instrument. Okay, so in that instrument, the electrons will be deflected to magnetic fields, and in that instrument there will be a pocket. In that pocket, we would have kept the source material itself. The electron would strike the source material, and it will not only strike in only one place, it will scatter through XY plane. So it will hit each part of the source evenly, by which we can do alternative to filament.
Okay. Banana Sindhu? Yes.
I had doubt in the isotropic and anisotropic so could you, if you completed the questions, could you teach us regarding that?
Okay. Banana.
And also I have doubt in the silicon wafer 111, 100, 110.
Yes, we can discuss right now. No?
We also wanted to do MEMS for me.
Okay. So in the silicon wafer, like this round shape of silicon wafer is present, and here is a primary cut which is bigger, and the smallest cut which is the upper side or something angle in between this secondary cut. Okay, so when the primary cut and the secondary cut is in 180 degree. Okay.
Ma'am,
Yes.
primary cut width higher than the secondary cut width, ma'am, in silicon.
Primary cut is length is bigger, and is the secondary cut is small. Okay, the small cut
Yes,
is
ma'am.
there. Okay, so if the angle between the primary cut and the secondary cut is 180 degree, it means here the primary cut and a small cut here, and this is round shape. So in that case, it is 100 N type. Okay, and if the angle between the primary cut and the secondary cut is 90 degree, so in that case it is P type 100. And if the angle between the primary cut and the secondary cut is 45 degree, then it is N type 111 plane. And if only the primary cut is present and there is no secondary cut, in that case it is P type 111. So have you got your answer?
So why we use the different types 111, 100?
Actually,
Why not?
111 is more density. So based on the application, we use this different type of 111, 100. Okay.
So for fabricating the chips, right, like 5 nanometer chips for processors, which one we prefer, ma'am?
Like if we can take a simple example, that if we want to take if you want to go for the P like chemiresistive sensor P type, we want the substrate. In that case we go for the P type material. And if actually it based on your application, it depends what you want to do.
So let us say we are trying to make a fabricated processor, microprocessor in phones or laptops. Okay. So at the time, which wafer do we prefer?
For which sensor?
It's not sensor, it's microprocessor, silicon chip. You have billions of transistors, right? Like
Yes.
Qualcomm Snap processor, Intel.
Actually, mainly we based on the application, we use this N type or P type. You have to find the which type of silicon wafer is suitable for your case, based on the application, right?
So here we use the application for computing, na? Computing high-end processor in our phones. Processor.
Actually, we have to. I have to also check which type of silicon wafer is in that in case.
I just had a doubt now, so that's why.
I only know that based on the application, we if we want the more density, then we can go for the 111 plane. And if you want, in our case, like we fabricate the P type or N type chemiresistive sensor. So using this type of application, we go for the P type or N type for the chemiresistive based sensor. And now we are coming to the question, the anisotropic and the isotropic. Banala Sindhu, can you explain what is isotropic aging? We also discussed in our previous session, I think, what is isotropic, what is anisotropic aging, and the example of an isotropic and anisotropic. Banala Sindhu?
Yes, ma'am.
I'm asking about the weight aging process, isotropic and anisotropic.
We both, I think.
Okay.
Ma'am, I didn't listen that, ma'am.
Okay. Actually, what happened in isotropic, it there is a two basic type of aging process, like dry aging process and the wet aging process. So what happened in dry aging process, we use some gaseous molecule or plasma to age that substrate. Okay. And what happened in wet aging process, we use some chemicals. Like for silicon aging, we use the TIMA process or cave-based solution. Okay. So for silicon dioxide aging, we use the buffer hydrofluoric acid. So in that case, when you go for the silicon dioxide aging, using the buffer hydrofluoric acid, so it age in all direction. So in all direction, it's aging the silicon dioxide. So in whenever the chemical aging in all direction, then it is called the isotropic aging. Okay. And when it is only a particular direction it age out, you can see in TIMA process, when we fabricate the pressure sensor, like that type of shape now. So we have to fabricate a diaphragm type. When we go for the fabricate the pressure sensor, then we have to age the silicon wafer and using the TIMA solution, and in a particular direction it age out. So whenever the chemicals age the silicon wafer or something else in a particular direction, then it is called the anisotropic aging. And when it is ages in the all direction, like we want to here the silicon dioxide is present, so when we dip the wafer into the BOF solution, buffer hydrofluoric acid, BHF, So in all direction the silicon is etched out. So this is the example of the isotropic etching. And when we go for the silicon etch using the TIMA solution, so in a particular direction, like this type of shape is present and here the diaphragm is present. So in a particular direction when it is etched out, so it is called anisotropic etching. So is it clear to you?
Yes, ma'am. And I also have another doubt in the photoresist area.
Okay.
So basically, we have the photoresist, right? Positive and negative photoresist, and most of the time, the positive and negative photoresist follows same procedure like spin coat, soft bake, UV expose, hard bake. Like, but in regarding the SU8, the procedure differs, right? First we do soft bake and then hard bake. After that you will expose to UV, right?
Then we go for the development, then go for the baking process like greater than 125 degrees centigrade.
Okay. So whether SU8 process differs upon application, ma'am, because yesterday we attended the problem solving session, and in that session I asked the same regarding SU8. That he mentioned that the SU8 procedure like you have first soft bake and hard bake, and then you have photoresist developer, right? It will differ upon the application. Like SU8 is used for creating the channels for drug delivery, right? Drug screening. The interdigitated electrode. In that, SU8 will follow the soft bake, hard bake, and photoresist mode. In other application, SU8 will follow soft bake, and as normal positive or negative, it will follow first soft bake, then photoresist development, and then hard bake.
Actually, what discussed in the lecture video, when we go for the positive or negative photo, SU8 is also a negative photoresist, but here the main difference is which is discussed in the lecture video, that for the positive and negative photoresist we are using this process, that we go for the soft bake, then we go for the UV expose, and after the UV expose we go for the development, and then the hard bake process is done. So then we go for the etching process. But only for the SU8, this it is discussed in the lecture video that we go for the soft bake 65 degrees centigrade, then we go for the hard bake process, which is 90 degrees centigrade.
Okay. So basically, you are saying that for only SU8 we go for first soft bake.
Soft bake. Actually, the temperature different. You can see na, like for positive and negative photoresist, the soft bake and soft bake temperature is 90 degree na, 90 degree for 1 minute.
Hot plate.
Okay.
Yes,
And for
ma'am.
SU8, what is the temperature? For soft bake, the temperature is 65 degree na. Then we go for the 90 degree. So here 90 degree temperature is called the hard bake process. But for positive and negative photoresist, the hard bake process, the temperature is 120 degree, right?
Yes,
So
ma'am.
here you can see the difference. It is telling that it is soft bake or hard bake. But what about the temperature? At first 65 degree, then we go for the 90 degree. So only the name is different.
So you are saying only the name is different,
Yes, actually, I'm.
but 1 minute. I had if you consider the assignment question in week 8, the SU8 procedure is different from what sir had taught in week 4. And had taught in week 4, right? Spin coat, soft bake, hard bake, UV exposure, and then you again bake at 125 degree or above. But
Yes.
in week 8 assignment, it is saying that first soft bake, and then UV exposure, and then hard bake. So both are SU8, but the procedure is different. So that's why I am asking.
here you have to notice the temperature. I think you have to focus on the temperature. What is the temperature of soft bake and hard bake for the AC weight, and what is the temperature for hard bake and soft bake for the positive and negative photoresist.
Ma'am, no ma'am. In if you watch the week 4 lecture, okay, the same SU8 as you mentioned, soft bake is 65 degree and then hard bake, and
Yes,
after
90
that,
degree. Yes.
yeah, and after that the photoresist development, and again you bake at above 125 degrees Celsius. Okay.
Yes.
This is the procedure that I have mentioned in week 4 video. But in week 8, and there is an assignment question regarding SU8 procedure. Okay.
Okay.
The order of the procedure. In that order, they mentioned first soft bake. This one is right. And
Okay.
then here they mentioned UV exposure. But if you watch the week 4 video, UV exposure comes after hard bake. But
Yes.
in week 8 assignment question, soft bake, then UV exposure, then after that only hard bake. So both are SU8. In week 4 also the same SU8, and week
So,
8 also same.
Have you seen the application for both? Same, they are using the AC weight for the same application, or the application is different?
In week 4 they are using that for creating microfluidic channels. No, for drug screening. Okay. Around the interdigitatory electrode they are building a walls for drug screening. Okay, so that is the application in week 4 SU8. In week 8 it is different.
It can be possible that for different application they are using this process.
Okay. So I also have a doubt. What is annealing in SU8? Why do we use annealing? Because we are using the soft bake, hard bake, na? Then why we again go for annealing?
Annealing is a temperature treatment. Like if we want to remove the defects, na, so in that case we are giving some temperature so the defects can less. So that's why we are using annealing. It is a temperature treatment.
Okay. So we use annealing for only for SU8 or for positive or negative photoresist also?
I think it can depends. Like if the defect is more, so in that case you can use the annealing. In different process also we can use the annealing. It is the only heat temperature treatment process.
Okay. So after the acetone dip, we go for annealing, or we go for annealing and then acetone dip? Which one? Which is the right one?
Actually, what happened when we dip into the device into the acetone, it removed the photoresist now. So if you want that photoresist, you want that the defects of photoresist will remove or it is less, then in that case before removing the photoresist you have to use this annealing process. Actually this process, it depends upon the application where you want to want the positive the photoresist will remain. If you want the photoresist will remain and we want to less the defects of this photoresist, then what if we dip the device into the acetone, then the photoresist will gone. So it depends. If you want the photoresist will remain, then before dip the acetone you have to apply this process.
Yes, ma'am. Understand.
Because once you dip the device into this acetone, then photoresist will gone. It is I think the photoresist remover.
Yes, ma'am. Yes, ma'am. Okay. So basically, we depending upon the application. right?
Yes.
So we- That's my question right now. If I have more question, I will ask in between.
Okay. So this is our question number 13. Which one is correct? So in E-beam evaporation, source holder material should be conductive. In e-beam evaporation, source holder material should not be conductive. In e-beam evaporation, source holder material should be conductive. And in thermal evaporation, source holder material should be conductive. In thermal evaporation, source holder material should not be conductive, or none of the above.
So basically here option 2 and option 3 is the right one.
Okay. Banala Sindhu, what is the right answer?
Option 2, ma'am.
And there multiple option is right. And what about the third option?
Third option, as you said, that thermal evaporation, right? The source holder material should be conductive to transfer the heat between the source and the holder.
Yes.
And regarding the E-beam, we are deflecting the electron beams to strike directly on the source material. We don't want source holder to be necessarily conductive.
Yes. But in thermal evaporation, we need the conductive source holder. So that's why the current will flow through it and it will hit, and then the source material which we want to deposit, it will evaporate and it will deposit it on the substrate. So option 2 and 3 is the right answer. Okay. Here the question number 14. In which process wide variety of material can be deposited because material is put into the vapor phase by a mechanical rather than a chemical or thermal process? Thermal evaporation, the first option is the thermal evaporation, second option is the sputtering, third option is the e-beam evaporation, and the fourth option is CVD.
So what is CVD? Chemical vapor deposition.
Yes.
So sputtering.
Okay. Banala Sindhu, what is the right answer?
No, ma'am. I think it is only the bus who put into vapor phase by
Thermal evaporation or e-beam evaporation, ma'am.
But here phased by a mechanical rather than the chemical or thermal process. The question is among these four options, which is mechanically deposited the material. Not the chemical or thermal process. Banana Sindhu.
Definitely sputtering.
Okay, can you explain why?
Basically, the sputtering is like by dislodging the atom through force, right? And here we have the unlimited number of materials can be deposited using sputtering rather than thermal. In thermal, the material is limited because the source holder is not can't withstand materials with a high temperature, right?
Actually, here the argon ions is sputtered on the target material. Then it is the source material which we want to deposit. It is coming out from this target and it is deposited on the substrate. Okay,
Yeah.
so the right answer is this. Banana Sindhu, have you got the answer?
Yes, ma'am.
Which of the following metal is not used in vacuum metallization? Aluminium, nickel, chromium or sodium?
Vacuum metallization. Now, what do you mean by vacuum metallization? I don't know.
Actually, here I am telling about the PVD system metallization. What type of material we used for the deposition technique? If you want
Ah, okay, okay. It is PVD.
Chromium, ma'am, not used for it.
Why don't we use chromium?
I think you heard about the deposition technique where we prepare our the contact pad using the chromium and gold. Why and what? So why we use the chromium for increase the addition of the gold, na? So for the metallization process we use the chromium, also the gold.
Okay, ma'am.
I think it's sodium.
Yes, the right answer is the sodium.
But I don't know how. Because aluminum, which can be deposited by welding or sparking, nickel also can be deposited. So
By thermal
chromium
also aluminium, nickel and chromium, all three you can deposit
but
it.
why don't you use sodium?
Actually, mainly sodium chloride. This is the chemicals now we use for chemical vapor deposition technique.
Okay. I see.
Which of the following is not a heating source in metallization? Convection heating, resistance heating, induction heating, electron beam heating.
Convection.
Okay. Vanilla Sindhu.
Ma'am, maybe induction heating, ma'am.
No, the right answer is the convection heating. Energy of an electron is up to dash in electron beam heating. 15 eV, 15 keV or 30 eV or 30 keV.
15.
So then what is the main difference between the positive and negative photoresist?
What, ma'am?
What is the main difference between positive and negative photoresist?
So basically, positive and negative photoresist, the UV exposure will remove the different regions.
Like,
For example, when we want to create an island, we go for negative photoresist.
what would happen if we use the positive photoresist and then we go for the UV exposed, and when we go for the developing process, then the exposed portion will what? It will become harder or it will etched out.
Basically, in positive photoresist, the unexposed area would be stronger, and the remaining area would be weaker.
For negative photoresist,
Negative photoresist, the unexposed area would be weaker, and the remaining area would be stronger.
okay. And what about the bright field mask and the dark field mask?
So, bright field mask. How to say? So, in bright field mask, actually, the when we want to create structures like interdigitatory electrodes, right? Then we use the bright field mask, like creating an island, above the surface of the substrate. And when we want to create a hole, we go for dark field mask, like removing a certain portion.
Okay, but tell me now, if if you want to make the ID pattern, okay, if you want to transfer an ID pattern and the pattern is in dark shade, or the chromium is there, the pattern is in dark shade and the remaining background is transparent, so what type of mask it is? Background is transparent, only the structure you need, it is in dark.
Background is it is bright field mask,
Because
we are covering the only what region we want to create the structure similar like the interdiscrete electrode, and that only we are covering, and basically the remaining area we are not exposing, right? So basically in bright field mask only the regions we need the structure will be covered.
yes. Good. Now tell me, what is the answer of this question number 70? Energy of an electron is up to 15 kilo keV.
15 keV.
Yes. In PCVD, deposition occur at a dash temperature. First option is higher, second option is constant, third option is increasing or lower.
What is PECVD?
Plasma enhanced CVD. At first tell me, what is CVD? What happened in CVD system?
I don't know CVD. I'm not
In
sure.
chemical vapor deposition, what happened? We take there is there are different type of chemical vapor deposition technique is present, like atmospheric pressure chemical vapor deposition, low pressure chemical vapor deposition, and also the plasma enhanced chemical vapor deposition. Also the metal oxide chemical vapor deposition is present, which we have used for the deposit the 3,5 material. So what happened in we are taking a simple example of atmospheric pressure chemical vapor deposition. There are 3 zones. So if we take the chemicals and we put the chemicals in the different zone whatever we need, and we set a temperature which is near or larger than the greater than the melting point of that chemicals, and then we flow the some carrier gas like some argon or some argon nitrogen or something. So in that case, when we increase the temperature beyond the melting point of the chemicals, then it start to vaporize, and then it chemically different molecules there are taking, and also then it is chemically then it start to react, and it prepare some other molecule. Like if we go for the MO2 deposition, we are taking the MO3 molybdenum oxide and also the sulfur, and we go for beyond the melting point of the MO3 and the sulfur, then it start to vaporize, then it start to react, and it prepare the MO2. So, and using the carrier gas, it is flowing, and also it is deposited on the substrate we want. Okay, so this is the simple example of the atmospheric pressure chemical vapor deposition. Now here it is a compression type technique. So in atmospheric pressure chemical vapor deposition, some temperature is needed, and also some for low pressure chemical vapor deposition, some different type of temperature is needed. Now we are coming to the plasma enhanced chemical vapor deposition technique. But here the question is, in PCVD deposition occur at which temperature? It means in higher temperature we go for the plasma enhanced CVD technique, or we need the constant temperature for plasma enhanced CVD, or the in increasing temperature or the lower temperature. actually in PCVD now we are in need lower temperature. That's why we go for the PCVD. In lower temperature we can operate this device.
Okay, ma'am. Okay, low temperature.
Now the question we already explained, that what is the mechanism of sputtering. Can you explain again?
What, ma'am?
What is the mechanism of the sputtering system? How sputtering is working?
Sputtering. Sputtering involves first we need to create the environment, as we said. So for creating the environment, we remove the atmospheric pressure and make it as a vacuum, and then we make the environment high pressure by inserting the argon gases, which will basically collide with the target material by exciting those gases, and that target material will get displaced from its position, and it will go and deposited on the substrate layer by layer. Is it right, ma'am?
Yes. Banana Sindhu, can you explain what is the mechanism of sputtering? Do you have any doubt?
No, ma'am.
Can you explain how the sputtering system works?
Ma'am, I have no idea. Ma'am.
But Suthar already explained. No?
It is like very easy process actually.
Ma'am, sputtering is deposition technique, ma'am.
Yes, there are three types
The
of
metal.
physical vapor deposition technique, like sputtering, E-beam evaporation, and thermal evaporation
E-beam
system.
evaporation, thermal evaporation, sputtering or deposition of metals. That is
Yes.
deposition technique is ma'am.
Yes.
Mm.
So what happened in sputtering?
In sputtering, when mm, ma'am, I
Sputtering.
have-
Yes, tell me. And sputtering.
ma'am, I have small idea on that, ma'am. I do.
Yes, if you tell me. The basic mechanism I want to know. What happened?
Yes.
Like there is a target and the substrate is below and the argon gas is flowing, then it hitting the target, and from there the molecule is coming and it is deposited on the substrate. And we have
Yes,
to
ma'am.
maintain our environment also, like the pressure and temperature, whatever we need, the environment we have to maintain, and this is the basic mechanism. Now you got your answer, Banala?
Yes, ma'am.
And this is also the simple question, the difference between evaporation and sputtering. So what is the main difference between these two techniques?
In sputtering, there is the involvement of the argon gases we insert in the environment. But in evaporation, we just maintain the vacuum or maintain the pressure.
And also we need the substrate holder and the material,
Yeah.
and we heating the source holder.
Ma'am,
And
E-beam evaporation is also called as E-beam deposition, ma'am.
yes, E-beam evaporation.
Why, ma'am?
Because here we use the E-beam, and then E-beam is going to the source material, and then it heated out and it vaporized and it deposited on the substrate. And what happened in evaporation, thermal evaporation, we flowing the current through the source holder, and it's heated out, and the material is kept in over this source holder material, and then it start to vaporize, and it deposited on the substrate. Okay, but we have to keep the material like that. The source holder material melting point should be lower than the source material. So the only the source material which whatever we want to deposit, it will vaporize and it will deposited on the top of the substrate. And what happened in sputtering system? In a sputtering system, we maintain the environment, then we flowing the argon gas, and it's heated out the target, and the molecules in the target, it is coming out from there and it is deposited on the substrate. So now have you got the answer?
Yes, ma'am. Yes,
Yes,
ma'am.
ma'am. Yes, ma'am.
So the question number 21 is, advantages of sputtering over E-beam evaporation is device damage from X-ray generated by electron beam evaporation is avoided. So it is true or false. So why here?
True.
Okay, Panala Sindhu, what is the right answer?
True, ma'am.
Now coming to the question number 22. Oxygen plasma is used for surface activation. Second option is surface cleaning. Third option is bond PDMS membrane to the glass substrate. And the last option is all of the above.
So all of the above.
Okay. Banana
Yes, ma'am.
Sindhu.
All of the above.
So now coming to the question, what is plasma? What is present in the plasma?
Ionized energy particles containing oxygen, nitrogen, ionized atoms, electrons.
Yes. Banana Sindhu, have you got the answer?
Yes, ma'am.
Now coming to the next question, question number 24. The process flow of oxygen plasma is turn off the vacuum pump, then turn on the RF power, then supply the oxygen into the chamber, then turn off the RF power, then turn off the oxygen supply into the chamber, and then turn off the vacuum pump. And the second option is first supply the oxygen to the chamber, then turn off the vacuum pump, then turn on the RF power, then turn off the RF power, then turn off the oxygen supply into the chamber, then turn off the vacuum pump. And the last option is the process flow of oxygen plasma is turn on the vacuum pump, then supply the oxygen into the chamber, then turn on the RF power, then after working turn off the RF power, then turn off the oxygen plasma into the chamber, then turn off the vacuum pump. So at first go through the question carefully. Try to get the
So
answer.
I got the answer. Third option.
Okay. Banana Sindhu.
Ma'am, I think second option.
Can you explain, please? Can you explain?
To first to create the process flow for oxygen plasma, we will turn on the vacuum pump, right? Because in that machine we need to create the environment by removing the molecules of the air, and then there will be two holes in that machine, and through one hole oxygen will be supplied and another hole vacuum pump will be activated. So first turn on the vacuum pump, second the oxygen will be inserted, and then we turn on the RF power. And turn on the RF power, and if we kept the PDMS, so it will get bonded and separate activated. it will turn off the RF power, and then you will turn off the oxygen supply, and then finally you turn off the vacuum pump.
Good. So this is the right answer, option 3. Banana Sindhu, have you got the answer?
Yes, ma'am.
Yes. So first we have to turn on the vacuum pump. So when the rough vacuum is generated, there we supply the oxygen into the chamber. Then after giving the oxygen into the chamber, we have to turn on the RF power. So we have to give some power. So what happened when we give the power? In the plasma, what happened when we give the power now? So electron from the outer cell, from the lowest energy level to it moves to the higher energy level. So after that, when it is release the energy, it's coming back to the higher energy level to the lower energy level. So in that time you can see the color change of the plasma. So it based on the lambda, na, whatever the electron is moving from the lower energy state to higher energy state, then after losing the energy it is coming back to the lower energy state. In that time they release the energy in the form of H nu, like. So in that case you can see the plasma whenever you go for the oxygen plasma process. Some pink color is present for the oxygen plasma. So after the work, the oxygen plasma process, we have to turn off the RF power. Then we off the oxygen supply into the chamber. Then after this we have to off the vacuum pump. So the third option is the right answer. So the next question is, in oxygen plasma the reflecting power should be low or equal to 0. It is true or false?
True.
Why?
The reflecting power will that should be kept minimum.
Why? Number question is why it is minimum or 0. If it is greater than the incoming, it's mean the what is the from the source the power is coming. If the reflect power is greater than the initial power, so what happen in that case? So it will coming back to the source now, so it will destroy the source. That's why we have to minimize the reflecting power. Now the question is, maximum detection angle of IR detection distance sensor is 25 degree, 35 degree, 45 degree or 55 degree.
It's option 2, 35.
Banana Sindhu, what is the maximum detection angle?
Ma'am, no idea, ma'am.
Actually it is 35 degree. Now the detection distance of, actually all this question is already discussed in the lecture video. You have to go through this lecture video. Okay.
Okay, ma'am.
Okay. So detection distance of IR based distance sensor is 0.22, 0.2 centimeter, 0.22, 2 centimeter, and 0 to 0.2 centimeter, 0.22, 2 centimeter, 2 to 30 centimeter, or 30 to 40 centimeter. So what is the right answer?
Option 2.
No.
0.222 centimeter.
Actually it is 2 to 30 centimeter.
Okay, 222.
Application of IR based distance sensor is security product, obstacle avoidance, and industrial automation control, etc., or all of the above.
All of the above.
The mold is made by silicon, silicon dioxide, glass, or all of the above.
All of the above.
No.
Silicon.
Yes, silicon mold is used.
All of the above, ma'am.
No. The answer is silicon.
Okay.
Ma'am, silicon dioxide is used, ma'am. Glass also.
It is only an oxide
Actually-
SiO2.
The mold is used for the microfluidic devices. Now it is silicon. At first, in the silicon, we have to use the photolithography process, and we have to make that pattern, and then we have to deposit it the PDMS. Then we have to cure this PDMS from the silicon wafer, and then we go for the bonding process. We go for the bonding process where we bond between this PDMS to this glass substrate. Okay. So in that case, we use the silicon mold. Have you got the answer?
Yes, ma'am.
Yes, ma'am.
So the last question is, if we want to measure the impedance of live cell, what type of structure we need and why?
We need to create a well around an interdigitally electrode.
Okay. And in which temperature the live cell can survive?
The life cell is same as like our body, normal body temperature, around 25 or 27 degree. It should be kept at temperature. For that we use the micro heater, right?
Yes, we want micro heater to maintain this temperature. And what about the temperature?
I think the temperature should be around 25 to 27 degrees.
No, it is 37 degrees centigrade.
Okay, 37.
37 degree. So we are ending our session here. So next we will meet next Tuesday 7 to 9 p.m.
Ma'am, before that I had some personal questions.
So you can directly mail me.
Ma'am?
You can mail me now.
No, just regarding the NIMS future, because I thought I need to go for NIMS by writing the gate exam and facing the quiz.
Okay. So you want to discuss some question?
Yeah, discuss regarding that. So that's why I asked. If you have time, okay. Otherwise, I will not.
No, you can mail me. Or in the YouTube also you can question there. I will give the answer.
Okay, fine.